Awesome. Good morning, everybody. I'm going to take you on a journey, a more of a journey of exploration. And my hope is that you will leave with some ideas, some thoughts, and more questions. So before I begin, I think most of the people I've interacted with over the past yesterday night and today has been focused on enterprise or information technology security. How many here have worked on operational technology security? Good, great, thank you. So what I want to talk about today is how do we think about applying artificial intelligence to securing critical infrastructure? And critical infrastructure, primarily, that is the bloodline, or that's absolutely essential for the AI innovation that we are living through, and that is the power grid. Without power, without energy, none of this, none of the cyber side of things would be possible, nor any of the AI, ML advancements that we are seeing right now. So before I begin, I want to sort of set the stage. I am neither a cybersecurity expert nor an AI ML expert. I'm a power engineer. I'm an electrical engineer who has thought about securing the grid, the cybersecurity of the grid, for, I want to say, a last decade or so, applying all kinds of concepts, including AI ML, game theoretic approaches, optimization approaches. How can we secure this critical infrastructure, essentially? So just a bit of a primer on why we are talking about securing the grid today. If you look at some of the statistics that are coming out, the US electricity consumption is going to hit almost 4.2 billion kilowatt hours by 2026. And 27% of that demand growth is because of AI and data centers. So if we are hoping to continue our cutting edge position in the domain of AI research and the advancement of AI, we cannot neglect the electric grid that sustains this. The data center consumption globally is going to be almost 8%, a 3% jump by 2030, which is substantial. And how can we think about applying artificial intelligence to the security of this critical infrastructure? And that's my hope, that you would walk away with some thoughts and some ideas. As you are working on developing your own mechanisms of AI ML applied to security, maybe it is enterprise security, maybe it's information security, maybe it is application security. What I want to give out today is what are the challenges we in the industry who are focusing on power grid security are facing? And maybe you have ideas that you can bring to us and help us sort of advance the state of security on operational technology. So before I begin, just for those who are not aware of how power grid works, just a bit of a crash course, if you will. On the left side of the screen, you can see the generation side of it. It's a mix of generation from nuclear to hydro to coal to wind or solar, all kinds of generations that get transmitted over transmission lines to a distribution substation, which is your neighborhood substation, which then gets transmitted via distribution lines to your homes and to your data centers and to your commercial buildings to power the load. All of this infrastructure is governed by controllers, computers, if you will, from small computationally powered computers to big HPCs that model these systems at scale, essentially, that run real-time simulations of the grid. All of these are attached to some sort of networking, whether it is a flat network that is isolated from the rest of the world, or in case of a Nest thermostat, maybe at your home, or a water heater at your home, or a solar panel at your home. Those are connected to internet via the OEM's own APIs and cloud services and things like that. So how do we think about security in a situation where the grid is no longer isolated? It is no longer air-gapped from the rest of the world. The devices that operate and run the grid are connected to the internet, at least on the distribution side of it. So how do we think about security in a situation like that? It is opening up attack vectors that we have not seen before, that we do not understand, that traditionally is not the wheelhouse of power engineers. And how can we help the system operators and power engineers make the right decisions? about the design of the system to its operation to incident response to recovery, all the way to the end, essentially. So with that baseline, just a view of the rising cyber threat. I'm not sure how many of you have heard about. I'm sure most of you have heard about some of the major incidents in the recent years, the 2015 and 2016 cyber attacks on the Ukraine power grid. There was a 2019 attack on the firewall for a lot of the American power grid systems. The latest 2023 attacks on the Ukraine grid because of the Russia-Ukraine war. There is an increasing escalation of cyber attacks on utilities worldwide. Almost 47% of all cyber attacks on the US system is on utility sector, is targeting critical infrastructure. And there is just the cyber attack growth year over year in Q3 of 2024 was 234%, essentially. And the latest Reuters report says almost a 70% increase year over year, October of last year, essentially. So with this rising cyber threat and the importance of critical infrastructure and power grid, how do we think about cybersecurity of the grid, essentially? So before I jump in, I want to expand the horizon a little bit more and think not just about cybersecurity, but cyber resilience. What do I mean by that? While security focuses on your traditional prevention and defense of the grid or your system itself, the resilience part of it thinks about all your defenses eventually are going to fail. There is going to be a successful attack. How do you withstand? How do you respond? How do you recover? And how do you adapt for future attacks? And that's the area that I want to focus on today. Not just the security of the grid, but what is the cyber resilience of the grid? And how can we think about cyber resilience of the grid? And where can AI/ML approaches help with the cyber resilience of the grid? So before I go into how we can use AI/ML, and I have some examples that I can talk about, how can we use AI/ML to enhance cyber resilience? What is the problem with cyber resilience of the grid? What is the problem that we are answering? So the first grand challenge, if you will, is there's a rapid increase in the scale of the number of devices that are connected to the grid. Traditionally, before you had your home was not necessarily connected on the internet, your Nest thermostats or your water heaters or any of your smart EV charging infrastructure, if you will, or your solar panels, these were not on the internet, but now they are. And these devices play a huge role in the operation and maintenance and the reliability of the grid itself. So how do we think about security of this critical infrastructure, considering that the number of devices that are attached to the grid that can have potential impact on the grid are increasing rapidly, exponentially, if you will. The second is, with the scale in the devices and the data comes the diversity. The vendors for a lot of the behind the meter, if you will, devices are all from all over the world. They are not just US-based, essentially. Your inverters or inverters for your solar panels or your EV charging infrastructure, they can get manufactured anywhere. So the supply chains for these devices are pretty diverse and pretty worldwide. And how do we think about security in a situation like that, where you cannot actually control who purchases what devices? The utility might be able to control what devices and what vendors they work with and what devices they use in their systems. But for an average customer, it is open worldwide. And how do we think about security in a situation where you cannot control your supply chain? The next is, and here's where it gets a bit different than your traditional information security, is this complex interaction between the cyber or the communication side of it and the physical. And by physical, I mean the grid that essentially operates, and there's a power flow happening on the network. And there is an impact of a cyber control or a cyber command on the cyber layer of the grid on the actual physical systems happening underneath it, which has security implications, which has safety implications, which has service delivery implications, business implications if the power were to go out. How do we think about cybersecurity in a situation like that? So the cybersecurity and cyber resilience of the grid cannot be thought just from the point of view of information security or data security. It's also security of the underlying process which it is governing and running on. So with that, the next one is another critical one, which is kind of unique to operational technology or power grids, is the trustworthiness and timeliness of the decisions. A lot of the control processes, if you will, that govern the power grid can happen at millisecond or less than a second scale, time scales. A time scale that a human cannot actually make a decision, especially with the scale of data, with the diversity of devices, and the complex interaction of cyber-physical systems. You cannot make a judgment call in less than a second on what should be the correct outcome or what should be a correct response on the grid if there was an event, essentially. So the timeliness part is critical. And the second is trustworthiness. The decisions that I'm making, they have immediate process or control impact on the system. How do I make the right decision? How do I make the decisions knowing full well my cyber layer and my physical layer? And there are not many people who understand both cyber and the physical layer. And how do we help those people to make the right decisions? I'll give you an anecdote. I was involved in a project a few years ago that focused on recovery of the grid, of a large-scale US grid after a cyber attack. How would you do that? You have 7 days. That was our objective. You have 7 days to recover the grid if it went down because of a cyber attack. We brought in the power guys. We brought in the cyber guys. We created a cyber range, if you will, a testbed environment, asked them to exercise the scenario, build the whole grid, took it down after a red teaming exercise, and now came in your traditional power grid people, and now came in your traditional blue teamers trying to restore the system. I kid you not, if you talked to the 2 people there, one a cyber guy, one a power guy, and you told each of them, go and turn on that switch, they will do completely different things. One will turn on a power switch, another will turn on a network switch. And that is the world we are living in. There is a huge disconnect between these 2 infrastructures. And we need mechanisms and people and technology that can help make sense, not just on the cyber side, but also on the physical side for us to make the right decisions, essentially. So with that, I'm going to jump into how we can use AI. What are the opportunities that AI provides that can help answer some of these challenges? And I'm going to walk through a cycle, if you will. How can we prepare the system, or how can we design the system at the initial stages such that we inject cyber resilience into the design of the system, or come up with better design approaches for the system? The second is, how do we defend in a situation like that? Third, how do we respond in a situation like that? And then how do we recover in a situation like that? So with that in mind, let me give you the first example that we have explored is predictive risk modeling. So analyzing historical breaches, if you have historical data, which is very hard to get on power grid infrastructure, historical breach data, can you learn and explore new topologies for a more resilient network? Can you figure out, can you discover, can you explore novel failover mechanisms, not just on your power network, but also on the cyber network together as a combined network? So one of the examples that you are seeing here, we use the graph recurrent attention network, which basically captures not just the spatial properties of the both cyber and the physical network, but also a temporal property of the cyber and the physical network. As the network changes, as events are happening on the system, as the topology changes, how do you capture that information such that you can do better design next time, such that you can implement better failover mechanisms at that time? Along with that, one of the other challenges that we run into in the power sector is security by compliance. Just because you are complying to standards and regulations and policies does not mean you are secure. Compliance is not security. However, can we leverage the latest advancements in AI/ML approaches like the large language models to help automate and verify security for power grids? So one of the exercises that we did is we took a lot of the standards and regulations and policies that power grids need to comply by, ran it through a local LLM model to extract security properties, not just extract security properties, but auto-formalize it. And by that, I mean formalize it or model them into a mathematical formulation that you can use to prove whether your system, as configured, meets these requirements or not. And it will give you some level of proof and guarantees that, yes, your system meets these requirements. So how can we move compliance from a subjective assessment where somebody goes out, does a checklist of whether you have these controls, whether you did this, whether your policies and protocols follow these issues? Can we do it a bit more quantifiable, a bit more verifiable assessment? And that's where AI/ML approaches, like the large language models, can tremendously help. Next is, how do we do AI defense? A smarter threat detection. One of the differences between IT and OT infrastructure, especially for the power grids, is IT infrastructure is primarily focused on protecting the information. And that's the only information that you have that you can work with. The interesting part with things like power grid is you also have a physical system that gives you data that is governed by the physics, that is governed by physical laws, your Kirchhoff laws, your Maxwell laws, if you will. You can break information security protocols. You can't break the laws of physics. It will tell you the truth. It will tell you the ground truth. Can we leverage both the cyber data and the physical data to do a correlation and do better threat detection? How can we do that? We have looked at approaches like federated learning models, where we capture both the grid or the physical system data, along with that, the cyber layer data, and developed a correlation. Correlation to identify better anomalies that could have impact on your physical system, not just on your cyber system, and detection that can preserve privacy as well. Because you can think of yourself, right? You as a customer, you might not want to share certain information about your own system with the utility. But can we use privacy-preserving federated learning models that preserve a customer's privacy, but still contribute to the security of the overall grid? And how can we do that? So one of the approaches that we have leveraged is combining the cyber and the physical data through a federated learning model to do better detection. Better detection at a local level, your home itself, but also at the system level, at the utility scale in and of itself. Second is, yes, detection is good, but it's not sufficient. And this goes back to Sunil's talk today morning about system one thinking. There is detection, but there is no explanation to it. For a system operator, for a grid security person to make the right decision, they do not just need hundreds of flags telling them, hey, these are anomalies, with no interpretation or explanation of what does this mean? What do I do with these anomalies? How do I make the right decisions? And that's where we have leveraged explainable AI to augment the current detection techniques like the federated learning models to generate explanations for what does the detection mean. And simple techniques like LIME, which the video is showing on the top, is while the detection is happening, it is also giving you indications of all the vectors that went into the AI detection model, what vectors played the highest role in AI thinking that this was an anomalous traffic or an anomalous event. That gives the system operator much more confidence, much more information to make the right decision. And they can then accept it, or they can reject it. But at least there is an explanation of what is going on. So how can we use AI/ML to augment detection decision support in the real world for these system operators? Again, these system operators are power engineers, just like me. How to parse through the whole of network traffic and do the correlation between a physical event and a network event is a very hard problem. It's cognitively almost impossible for a human to sit at a screen and make that decision. How can we give them some sort of an actionable interpretable decision such that they can make better decisions on the grid detection itself. The next is, how do we withstand the attacks? There, you can do all your prevention as much as you like. You can prepare your system. You can have the best detection mechanisms, yet there are going to be impacts on your system. There are no security mechanism is 100% foolproof. It is going to fail sometimes. How do you withstand that situation? So there are two ways you can think about response. One is an automated response, and the other is a decision support response. The reason why I'm bringing automated response, and I know a lot of people will squirm using AI to do automated response on a critical infrastructure. That's like a no-no, and that is correct. However, there are situations where a human decision-making might not actually help you because, again, the timescales at which you have to make decisions are so small in millisecond or second scale, it's not possible for a human to make the decision. So the best you can do is have AI approaches that help you sustain through an attack, to withstand an attack, and do some sort of autonomous response at least at those timescales. So for that, we have used a model called actor-critic reinforcement learning. What that essentially means is, think of your home as a local model, your neighborhood as another local model, and you can have an AI agent or an AI learning agent, if you will, which is an actor at that local home level. At the system level, where all the load gets aggregated for a utility scale, you can have a critique model. So a lot of the detection and response for the local system, for your home, happens at your home level. However, to make sure that your overall system is bounded and overall system is secure and resilient and is riding through whatever is going on your system, there is a critique model that looks at the whole system and critiques the output of every actor underneath it. That provides you a very coordinated and trustworthy response mechanism where there are not individual local models making decisions in isolation. There is an overall critique model that's looking at the safety, security, reliability of the system as a whole. So one of the works that we have done is apply these to a local network where we did every home has an actor model, and every system at the larger scale, either a neighborhood or a utility, has a critique model that critiques the decisions of the underlying actor model, giving you an idea of how you can ride through or withstand or sustain an attack in an automated fashion at a very small time scales, essentially. So with that, the second approach is, again, another thing that Sunil talked about today is SOARs. Let's say a SOAR for operational technology systems. What does that look like? So the question here is, how can we help the incident responders on the grid to make the right decisions? What kind of information can we give them when they are doing incident response? The challenge here is the grid has to comply by number of standards and regulations and policies. Along with that, it has to comply by the current physical system state, the safety conditions. You cannot make decisions on the grid that could harm the safety of the infrastructure or the people. And to make real-world, real-time decisions in the field, accounting for the cyber and the physical layer, are you complying with the standards and regulations and the policy on the cyber side of it and the physical side of it? Along with that, are you complying with the physical system state? How can LLMs help make the whole SOAR process or augment the SOAR process much better? So what we have done is leveraging a combination of large language models with, again, a model of formal verification, where we ingest a lot of the standards and regulations, safety requirements of the system, and we parse through all the different requirements and formalize them, both on the physical system side of things. What are the safety conditions? What are the regulatory requirements that you need to meet? There are standards called NERC-CIP standards that govern at least the bulk electric power system in the US. How do we meet the standards and the requirements of the standards while doing incident response? So what I'm going to play is a brief video on assuming the intrusion gets detected. If the intrusion gets detected, you have a set of options that you can take as a response model for that particular incident. However, how do you know which of these responses will actually comply by your standards and policies and regulations and won't violate any of the physical state of the system? So this tool allows you to combine both your standards and regulation data along with the physical system response data to make the right decisions. It will tell you what are the responses that will satisfy all your requirements, all your constraints, and what are the responses that will violate some of these constraints. And how can you use this in the field for better recovery, for better response, for better predictive analytics that can help incident responders to make the right decisions in the field. The next is recovery. We did automated response. We did SOAR-based response. Now, how do you recover the system? Part of your system did go down. Maybe you do not want to worry about the recovery of the entire system, but you do want to worry about the recovery of your critical loads, your hospitals, your army bases, your fire stations. How do you think about recovery of these critical assets? And is there an option where AI/ML approaches can actually help you make better recovery decisions? The challenge with recovery after a cyber attack on the grid is much different than a challenge of recovery after, let's say, a flooding or a hurricane event, because you know you can still trust your cyber systems. You know your cyber systems are telling you the situational awareness it's providing you is correct and trustworthy. But the challenge of recovery after a cyber attack is you lose the trust in your system, in your data, in your configurations, in your devices. And how do you do recovery in a situation like that? What are my best recovery paths, not just for the physical system, but also the cyber system? You can put everything in manual, crank up all your power, and you might recover some part of your physical system. But from the cybersecurity perspective, you are still as vulnerable as you were before. And how do you handle, and what kind of support can you give to this recovery people that they can go out and make the right decisions? And the hope here is AI/ML approaches would be able to do recovery faster than what your traditional first responders or power grid recovery folks are able to do. So one of the techniques that we used was reinforcement learning with expert feedback. The way to think about this is you can train a reinforcement learning model a number of different states of recovery on your system model. There are decisions that power system engineers and your OT security people make to best recover both the cyber and the physical side of it. And many a times, these are in isolation. Can you train a combined reinforcement learning model, taking the feedback and real-world decisions from these first responders, and train an agent that hopefully will outperform the eventual expert in the field in and of themselves? So what we were able to show is the combined decision-making on a combined network, cyber and physical network, if given sufficient data with sufficient expert loop into it, will be able to recover faster than what an expert decision can make. But this is very much dependent on the amount of data that you have, amount of scenarios you are able to exercise, amount of responses, the correct responses you are able to get from the agents as well. So this is more of an exploratory work at this point, where we are trying to see what level of information, what level of expert feedback would we need, such that we can at least give a decision support tool to enhance and make the recovery faster than what would be traditionally. So I went through a whole gamut of from preparing to defending to automated response to recovery to helping decision-making in real-world incident response like a SOAR. So I want to leave you guys with some thoughts. And none of the techniques and none of the approaches that I presented, we are not claiming that is sufficient or is perfect or correct. These are foods for thought. These are food for thought as you are thinking about applying AI/ML approaches to your security questions. How can you help? How can you help critical infrastructure owner operators how can you provide them better tools and better approaches to do the right decision making? So the key thought I want to leave you with is securing the grid is a collective responsibility. It is not just a utilities problem. It is your problem, it is my problem, it is your organization's problem, because we all depend on the grid. If there are tools and approaches that you are working with, and if you are able to resonate with some of the challenges that I described, please feel free to come, talk to me. I would love to explore ideas on how it can help answer some of these questions. Maybe you already have approaches that you are working on. Maybe you are thinking of working on certain approaches where you think it can help some of the grid challenges. I would love to discuss more with you. Along with that, we can think of a federated model of security. And this is, again, crucially important because key part of cyber defense is going to be threat information sharing. How can we create trust? How can we federate trust across entities in the power grid? Whether it's a trust between a customer and a utility, customer or an aggregator, aggregator and a utility, a vendor and a utility. How do we federate trust such that they are open to sharing information? Without real-world threat information, without real-world data, it is very hard to apply these AI/ML approaches. However, AI/ML approaches can help you do this information sharing in a way that is privacy preserving, in a way that is actionable, in a way such that the eventual AI-based cyber resilience and cyber defense is going to be more than the sum of its parts. The total is going to be more than the sum of its parts. While we keep playing in isolation on defending your own system and defending your own information, defending your own infrastructure, working collectively together, the output and the information and the actionable insights that we would get is going to be much higher than what we in isolation would be able to do. So with that, I'm going to stop here. Please feel free to stop me in the hallway. We'd love to chat. And if you have any approaches and ideas, or if this triggered any thoughts for you, please reach out to me. We'd love to connect. So thank you.